we'll just that's what we'll be doing today. So, and I don't have bios on you guys, but I'll let you introduce yourselves. Okay, I think we're ready to go.
Sounds good.
All right. So I guess I'll get started. Hello, everyone. My name is Timothy, and I'm an application engineer here at the MATLAB. Today, we're presenting to you some ways on how you can make your code run faster in MATLAB, and this is how we're gonna do this by taking advantage of parallel computing and distributed computing. So when we talk about this, we want to first go into why we would even choose parallel computing and what benefits it gains, right? And so I think the real big obvious benefit that we have is that we're able to save time. Parallel computing allows us to run things, as the name implies, in parallel. And so we're able to do more work in a given amount of time. And as problems become increasingly more complex, and we'll see later too, as our data becomes increasingly larger, having these resources to leverage will allow us to significantly cut down on work. And we'll also see within MATLAB and Simulink the benefits that we're able to bring when we're enabling parallel computing within our tools. And a big portion of that too is we not only want to save time within our research, but we also want to save time within learning how to implement these solutions. And so we'll go over a little bit about how easy it can be to implement these solutions in MATLAB. As I mentioned a little bit earlier, the benefits of parallel computing are pretty obvious, but here are just some speed up times that you have for reference. Speeding something up by 2x times for the automotive test analysis. In their case, reduced the development time by 4 months. Discrete event models of fleet performance, saved their simulation time from months to hours, and some of the other examples here. So we have a real big cost that we can get back if we properly leverage some of the tools that we'll go over in this presentation. And so before even going into parallelizing your code, right, let's just talk about overall performance improvements, right? And so before we go into parallelizing, the first thing we want to do is optimize serial performance of your code, right? So running it as you would if you had no access to no other workers, just making sure that your code is as optimal as possible. Part of that and sort of the next step would be to analyze our code for bottlenecks, and we can do this using built-in timer functions like tick-tock or even the profiler, which I'll go into a little bit more later, just to kind of see where we can get the most bang for our buck. And then third, we can include our compiled languages. In this case, things like C, C++, they can be really helpful in helping to accelerate our code. Not all the time, but definitely some improvements can be seen. And really, when you implement all of this and at the end of the day, you still decide, hey, I need to take further advantages of the resources available to me, or the speed up that I'm seeing even after implementing the first 3 steps aren't enough, then we begin to leverage our parallel computing resources. So in MATLAB, there are a couple of different ways that we have parallel computing, parallelizing our code available to us. The first thing is with multi-threading, and good news for most of you guys here, if you are using MATLAB and you're using our built-in functionalities, things like FFT, or so on, some of those functions already have built-in multi-threading. So you don't have to do anything. You're already taking advantage of cores and threads if they're available to you on your machine, and you're already seeing some return for the effort put in. However, there is the second step, there's a second option here, which is more explicit techniques, and this is what we'll go over today. And these explicit techniques allow us to manage more control over the code that we want, but still be able to spread out the work over the workers that we're trying to utilize today. And so just a quick example of hopefully some of the benefits that we'll seek to gain in this presentation. We can see here in the top left graph, we have a desktop with around 20 workers available to us. On the top right, we have a cluster with 200 workers. And on the bottom right, we have an HPC cluster with 1,000 workers. And we can see that in the span of 2.8 minutes, we have a 5x performance increase compared to our cluster, and significant increase, almost a 50x increase from our desktop. So really powerful tools to make your work faster and easier. So for the agenda today, we'll kind of go in a sequential order of starting with your local machine and then leveraging all those resources until we exhaust them, and then how we can scale up further into the cluster and even the cloud. But really, we're talking a lot about we're not really addressing the problem here. So then the third part of our agenda is actually going into the data, because if you have computationally intensive problems, chances are you also have very memory-heavy data. And then on the fourth point of our agenda, we're going to talk about how we can accelerate our applications using GPUs instead of our local computer clusters. And then lastly, a summary and resources, and I'll kick it off to Lisa and the supercomputer group to share their presentations as well. So when we talk about parallel computing, let's have a visual representation of what it looks like. So here we have a PC with our parallel computing toolbox enabled for us. And on that PC, we have multiple cores. The very basic and straightforward image of this is we're putting MATLAB on each core to do the work that we want it to do. So very straightforward. And hopefully, and what we would like to see is, because the concept is so straightforward, the implementation is as straightforward. And we have three different flavors of implementations that we're going to talk about today, and they balance how easy they are to implement and use, and how much control over your code and your work allocation it gives you. And so the first option that we're going to talk about really is the easiest to use, and it gives you the least amount of control, and that's going to be our parallel enabled toolboxes. And to talk about this, we're going to go into MATLAB real quick and talk about a classification learner app. And essentially what this does is we have data taken from our phones, and we develop a machine learning app to read the accelerometer data and see, are you standing, are you sitting, are you laying down, so on. Now, this isn't really a seminar on machine learning or deep learning, so I'll skip really all of the technical parts of that. But I wanted to just go over real quick this apps gallery. And so this is where we're going to actually get started with everything. But if you see here, we have a lot of domains that I think you guys can really benefit from taking a look into. Here with machine learning, we're going to go ahead and choose our classification learner app to get started here. Give MATLAB a couple seconds. I'm going to start a new session from the data in my workspace. And in this case, if anyone's familiar with, for those of you familiar with machine learning, I've already gotten my data and pre-processed it and set it up in the right way to import it into our app here. And so what I want to do is I want to essentially train a machine learning model to classify these different human activities based on what I've fed into it. And so I can just choose all quick to train. I can choose any one I want, but this is just the fastest. And we can actually see here, we have the option to train it all, but next to it, we also have this button that says use parallel. And I can click it off if I wanted to, but the point of this presentation is parallelizing your code. So I'll enable it and I'll press train all. And what we're going to see on the left-hand side here, once it's finished loading, is we're actually going to see multiple models being trained at the same time. And the reason for that is because different cores on my machine are doing the work necessary to train each model. And compared to having done this in serial, where I have to wait for model 1, model 2.1, model 2.2 to train in a more linear or serial manner, I can now do this in parallel and have multiple models training at the same time. And really, the only thing I needed to do was press this use parallel button. And so we can see the real ease of use for this is that it's built-in functionality. It's implicit. It just works. No extra work for you to focus on. We go into here, there's another option that I want to show you, and this is going to showcase a little bit of a caveat to this whole parallelizing your code, but also show you another option to enable parallelization in your functions. So if I go ahead and open up the app here, we can see here that we have this app with some bubbles here. Essentially what we're simulating is we have cell phone towers that we can specify with the number here on the right-hand side. And each tower has a random range. And we want to generate the ideal coverage for this map given the towers that we're having. So this is an optimization problem. And I'm going to go ahead and run this in serial. And so we see it takes about 3 seconds. When I go ahead and switch this to parallel, essentially what we're doing in the code here, if I go through, right, is we're just passing in a use parallel flag, right? So again, just showcasing really you can either press a button if you're using an app or pass in just a single flag, and you're enabling MATLAB to take advantage of whatever parallel options you have available to you. But before I hit run, I just want to ask you guys a question here. How fast do you think this is going to be based on what we saw earlier? We have 15 towers. I believe my machine has 4 cores. That's any indication of. Okay, so we see some different responses here. So let's actually go ahead and check it out. Right. So I think everybody took a guess that parallelization was faster. But in this case, actually, it's slower, significantly so, actually. And a big reason for this is there's overhead associated with writing the data to the workers, reading it back from the workers, right? Just things that would be required in this case in an optimization problem. And because of this overhead and how simple our problem is, the cost is actually higher than the gains we would get if we parallelized our solution. So in this case here, we have 15 towers, so it's a pretty simple optimization problem. But if we were to increase the complexity here and change 15 to 50 by chance, we could see in the in the serial case, we take about 9.7 seconds. And now if we parallelize everything, we'll see something more along the lines of what we expect. And so here we have a speed up of about 1.12. And so we can actually see now, okay, because the problem is challenging enough, the overhead cost can be mitigated by the savings that we return. I bring this up because I want to let you guys know, really, parallelizing your code is not always going to be the solution for everything. And we'll go in over different approaches that we can take to speed up our code. But I don't want everyone here, going after this presentation saying, you know what, the first thing I'm going to do is I'm going to enable a use parallel flag, and that'll make everything faster. Because there is a lot of complexities and intricacies with the whole issue of accelerating your code that we need to first explore before just parallelizing everything. And just kind of as a shout out, if there are any questions that you guys have, feel free to either put it in the chat or even reach out to any one of us presenters from the MathWorks after this presentation. We're more than happy to kind of walk through, see what you're doing, and recommend more efficient ways to do things. I just wanted to take a quick minute now. So how do we know whether a toolbox or function is parallel enabled? And then where will the recording be available? I would like to rewatch this later. So the recording will be sent out sometime after this presentation. And for how we know a toolbox or a function is parallel enabled, I'll go ahead and address that right now. So if I go ahead and open our documentation, I think one of the functions that we saw that was parallel enabled was FFT, right? Fourier transform. So if you guys have looked at our documentation, you may be familiar with the great examples and the great syntax that they provide you. But on the bottom here, we have something called extended capabilities. And so if I go ahead and click on that, it actually tells me if this function is enabled for a thread-based environment, if I can parallelize it using GPU arrays or even distributed arrays. And this is just something that I wanted to showcase because I think it's helpful, especially going through this example. Documentation is a real great step that you can, documentation is a real great tool that you can leverage to help you in your parallelization efforts. If you're doing any work in these toolbox that are in the slide in front of you, good news for you, simple flag or a simple press of a button, you're able to parallelize your code. Now, if you're not working in those spaces, then these other programming constructs that we're about to go over are going to be what you might look into next. And so the second option that we have is still very easy to use, but allows you greater control over your code. And that's going to be par4 and batch. So this is more explicit parallelism. And what par4 actually does is it allows you to allocate your work onto the different workers. And in this case here, you can tell worker A to work on a set of problems, tell worker B to work on a different set of problems. And what's great about par4 is that MATLAB does all of this in the background for you. So again, kind of reducing your control, but making it rather easy for you. Easy because if you want to change from a for loop to a par4 loop, the only difference is setting a par at the beginning of it. To showcase this, the next demo that we're going to go over is going to be a parameter sweep. And if we look at the slide here, on the top, it actually says that this is an embarrassingly parallel task. And what we mean by that is something that's embarrassingly parallel is things that are independent in nature. So the iterations are independent of each other. The results are independent, and one iteration is not dependent on the results of another, like we saw in our optimization problem before. And the reason why this is embarrassingly parallel is because a lot of the overhead that we had with our optimization problem earlier is no longer present with these sort of independent tasks. So it makes a lot of sense, and we get a lot of return when we parallelize these sort of problems. So let me go ahead and select that demo here. Second. Okay. And so the first thing I want to actually do is run this code, but I'm going to go ahead and run and time it just to see how long it takes to run this example. And so we have this trust here that has a dynamic load, and we're seeing what the response is, and we have a plot showing us everything. But I press run in time, and this allows me to leverage my profiler tool. And the profiler tool will give us access to this flame graph that shows us essentially how much time any particular function is, MATLAB is spending its time in. So in this case, we have the param sweep as the main function, and we have a couple other function calls like plot truss or truss cantilever that's taking a significant amount of time here. In this case, 5 seconds and 6 seconds. And so if we look back at our first, at one of the beginning slides, right, we don't want to immediately go into parallelizing our code with a par4 loop. Right? We want to see if there's some other ways that we can accelerate our code here. And so in this case, this code's been provided to us. So we will just say, hey, we trust the person had good programming techniques, so we know that it's optimized for serial runs. So the next thing that we can do is you can see where we can get the lowest hanging fruit. So plot truss is the first function that takes a lot of time. And so if we go in and we actually see where plot truss is, it's at this bottom here, and we're just plotting. So not much efficiency to be had. But if we look at our next function, which is truss cantilever, right, we can see that we have one call here. But if we actually look at this for loop here, we're actually spending a significant amount of time in this for loop because we're iterating through and calling trust cantilevers quite a number of times here. In this case, the number of elements in a grid. And so let's see if we can switch that from a for loop and to a par for loop, see if we get any noticeable return. In this case here, I've gone ahead and run it. My flame graph is back up here. If we go back into MATLAB, we'll actually see we went from about 5.5 seconds that we spent in this for loop to 3 seconds. So almost a 2x improvement here. And all we had to do was change our loop from a for loop to a par for loop, and we were able to leverage built-in tools like TikTok and our profiler to easily find this, right? So really another great example here is we have a lot of tools built in that allow you to easily identify any bottlenecks that you might encounter or run into that you can resolve easily with par 4 or in the example that I showed earlier, a flag if you're able to pass it in. Let me go back to the presentation here and talk a little bit more about what's actually going on under the hood. And so in this case, we have a par for loop that iterates from 1 to 10. And so what MATLAB does in the background is it splits up the work into different, I guess, modules of work, and it spreads it out to the worker automatically. And as resources free up, MATLAB will automatically reallocate the work to workers that are free. And what's great about this is you don't have to worry about this allocation. You don't have to worry about how you're going to tell the workers which job to do, when to start a job, if the job is finished, if you have to pull the job. That's all done for you. So you're not given as much control because you can't specify the workers in this case, but you still have a very easy to use entry point into parallelizing the work that you're doing. We do have tips for leveraging par 4 as well. So these are some general hints and tricks that you can use to make the most efficient use of par 4. But if we go ahead and go back into our doc page, actually, I just want to spend some time and showcase something else as well. So within MATLAB, within our parallel computing toolbox, we have these parallel for loops. And we have a lot of great examples and resources to help you get started with par for loops. So things like how to convert your for loops into par for loops, how to ensure that they're actually independent and there's no dependency between the iterations, when to use when to use par for loops and when not to use it. So again, I really recommend taking a look at our documentation if there are questions that you have and how to parallelize your work. Let me just go ahead and close everything out first. Okay. We've talked about a lot of the basic applications of the very easy to use constructs that we have in MATLAB and even Simulink as well to enable parallelization of your code. There are more advanced programming constructs that give you really precise control over your workers, over the work that is distributed in memory that gets passed across. But for a lot of the people here, and for most of the people that even use our parallel computing toolbox, you won't run into this. So if you do, I would highly recommend reaching out to us at MathWorks. Sumit is a great point of contact because this is something that we can have a very long discussion over that unfortunately we will not have the time to go into too much today. So now that you've leveraged everything that you can and you've utilized everything on your desktop computer, you are still saying to yourself, this isn't enough and I need more. Right? And so now we can begin to scale up to external resources like a cluster or even the cloud. And so what are the advantages of taking advantage of a cluster hardware? Well, really the most obvious one is you have a lot more compute power. So you can speed up things a lot more, and you also have a lot more memory because you just have more resources to deal with. Another benefit is you have the capability to offload your computation. So earlier in the presentation, there's a bit of sitting around waiting for things to finish up, and that's because my machine was MATLAB was using my machine and saying, hey, look, you can't do anything until we finish this. If you're able to take advantage of other clusters, you can offload your computation, so it frees up your local computer for use. And in the spirit of parallelizing everything, now you're even parallelizing the work that you can do with multitasking, with freeing up your local computer to do other things while your cluster runs the computations in the background. So if we look at this scaled up paradigm of what parallel computing looks like with a cluster, we can see we have multiple machines like we saw earlier with 4 cores, but we just have more of them. And now we're just putting MATLAB on all of them. So a very straightforward concept. If you wanted to expand further up, you could even migrate this to the cloud. So in talking about the advantages, the first advantage was the ability to offload your computation. And to do this, you can use the batch command. And so batch allows you to submit batch jobs from MATLAB to your other workers or your cluster, and it frees up MATLAB to do other things as the computations are running in the background. So you send the batch job over to the head worker, and then it returns the results when they finish. If you wanted to specify for a parallel pool, all you would have to do in this case is call the cluster of interest, and then it will then send the batch job and then allocate that work over to the workers and then return the results when they're ready. So again, very straightforward and pretty intuitive. You can even go up and migrate to the cluster and cloud, and we have a very easy and interactive tool called the Cluster Profile Manager, and this allows you to easily discover clusters and switch between existing clusters as well. We recognize that there are a broad range of needs for parallelization, and especially when moving up to external environments like clusters or the cloud. And so MathWorks does support a lot of these solutions for you. And so I highly recommend either taking a look at the documentation when you have a chance, or again, reaching out to us because we want to be there to help you. We also have reference architectures enabled, posted on GitHub that it's free to download and free to use. So we talked a lot about really the symptoms of complex data, complex problems, but we didn't really address the problem. And in this case here, the problem will be massive amounts of data, right? We're talking terabytes or even petabytes of data that cannot fit on your local machine or your local memory. And so how can we address this problem? In MATLAB, there's a pretty elegant solution. We're going to talk about a couple of them. So tall arrays and distributed arrays and data stores. So in the upcoming slides, we'll talk about what they are, when to use them, and how to best leverage them. So distributed arrays, if you think about it in this context, it'll be you have access to a cluster that individually any one machine does not have enough memory to store all the data, but collectively all your machines have the capability to store all the data. And so distributed arrays will allow you to spread out your data over those machines where they fit, and then you can compute whatever computations you have throughout that cluster. And so this is really helpful when you have access to a cluster that has all the memory that you need. And again, distributed arrays allow you to not really have to focus on how to split up the data because MATLAB is doing that in the background for you. But if you wanted to work with out-of-memory data almost as if it's in memory, tall arrays are a really great approach for this. And so tall arrays, if you imagine, in this case, you have an array that's columnar data and it has a lot of observations. So if you imagine how that looks, you have a very long, almost stretched out matrix, and that's where the name tall comes from. And how tall arrays work is that MATLAB in the backend breaks up the data into different chunks that can fit into memory. and it'll scan through those chunks one at a time, and it actually performs an optimization to make the most efficient number of passes. And because it's broken up into chunks that can fit into local memory, processing the code is very similar, if not identical, to ordinary arrays. And so we have a demo here of predicting the cost of a taxi ride in New York City. Anyone's been to New York, taxis are abundant, and that there's a lot of data that comes in here, right? So in this case, we have a smaller sample of the data that we're working with, 12 different CSV files, but the data itself are gigabytes in size, or terabytes, I believe. So just to kind of run through, just to show you how to set it up, right? The first thing we want to do is set up the execution environment. So this is going to allow me to let MATLAB know, hey, look, I have a parallel pool called local. I want you to use it. So the first thing that we're going to do is create a data store. And so I mentioned that earlier, a data store. But what exactly is it? Well, we have a folder here of all of our data here, in this case, CSV files. And a data store essentially is a reference to where all the data lives, and it also contains metadata for how to read those files. And what's great about this is you don't have to have all the data in your memory now. Now all you have essentially is reference to where your data is living, and MATLAB knows how to read into it. So when it actually has to read into it, it has the capability to do so. And so we have functions here to help you work with the data. Right? MATLAB hasn't actually read in the data yet. It just knows where it lives. So we can call preview to get a sense of the first few rows, in this case, 8. And what's great about this is, as I mentioned earlier, working with these constructs, we want it to be intuitive to us, right? Just because our problems are more difficult doesn't mean our approaches to these problems have to be any more difficult. So we've worked really hard at MathWorks to make these programming constructs very easy to use, which hopefully you're picking up on that trend. And so working with this data store is the same as any other table. I can call into things like the variable names. I can choose which variable names I want. I can even change the format, and we can see now the data store has changed based on the code that we've given it. And so the next thing I want to do is put it into a tall array, right? And it's very easy to call. I can just call tall of the data store. And we'll actually notice something a little bit unique about tall arrays here. And I just want to give people a second here, maybe if they can see what I'm talking about. Does anyone notice anything different about a tall array than they would any other array? Cool. So very subtle difference, especially for those that haven't used it. But we'll actually see here, this tall array is an m by 5 table. And the reason for that is, as I mentioned to you, MATLAB's not actually reading into the data unless it needs to, because again, we're trying to really speed up the computation and free up your resources to actually do the heavy lifting. So right now, we don't actually need to know the data, so there's no heavy lifting involved. Again, just working with it very easily, we can use built-in functionality like hours, minutes, even mean to figure things out. No need to learn any new syntax. You can just use what you've been using for regular arrays, but now for out-of-memory data. And again, something I want to point out here, right? When we actually try to calculate the value of the mean of our array here, we see that the answer is a question mark and that the preview's been deferred. And so the reason for that is because we haven't called gather on it yet. If you remember the little animation for tall arrays, we're scanning through the chunks one at a time, but I told you that MATLAB's doing a lot of heavy lifting under the hood here. And it doesn't actually go into the data until you tell it to, and it needs to know what it needs to go into because it's trying to optimize the number of passes into your data. And to do that, it needs to know what operations it actually has to perform. And so once we actually call gather and tell MATLAB, hey, we just want the mean in this case, it'll go do that. And in this case, it says that there's only one pass of our data required. And we're then able to get our result here, in this case, around 15 for the mean. Now we have other best practices that you can look through in this script. But one thing I also wanted to point out here, you do have the option to do multiple variables, to call gather on multiple variables at one time. And we can see here in this case, still optimized. We only need to do one pass of our entire data to get the mean, the standard deviation, and the height. So you don't have to do a lot of fuss or worry. There's a lot of heavy lifting under the hood. Just utilize these data types, and you can get access to all of these great features and functionality. So that was it for the tackling the data-intensive problems. So let's talk about GPUs. And so GPUs are really great because they have a lot of cores, right? Like if you see your laptop, you may have access to 4 to 6 cores on your laptop at any given time. But GPUs have access to like hundreds of cores. The analogy that I really like to use for this is if you're talking about a CPU, each core is like a horse, and they do a lot of work, and collectively they can do even greater work. But if you look at a GPU, each core is like an ant, and individually it doesn't do that much. But when you have like thousands of ants, right, you end up running a $10,000 pest infestation bill. So you can see a lot of damage that can be done and a lot of impact that individual cores can have. So GPUs are really good for computationally intensive problems, but problems that don't require a lot of memory. We have different requirements for your GPU based on which release of MATLAB that you have, and we have a documentation page that really shows you everything that you need to get set up successfully. And if we imagine the paradigm for GPU computing, it's very similar to what we saw with the tall arrays, right? We have to first put it into the appropriate data type, which then gets sent out to a GPU device. Then we call it back in, and we're able to read it properly. Here's some applications that we can see getting sped up using GPUs. And I recommend, if you are using any of them, to try to leverage GPUs. In this case here, we don't have a very quick and easy enable toolbox like we did for the CPU, but rather we have things like GPU array and gather, like we saw earlier with tall arrays and gather. And so to showcase how to actually do this, I'm going to go into a demo here, solving a second-order wave equation using spectral methods. And so what I actually want to do here is compare the selected files here. And we'll see on the left-hand side, this is code that we've written out for the CPU. And on the right-hand side, we'll see the code that's been written for the GPU. And so the first difference that we'll see is we're sending the data to the GPU, right? We're marshaling it in as a GPU array. And using GPU array is great because it takes care of sending over the data to the GPU and making it so that the GPU can see the data. So doing a lot of the heavy lifting in the background, even with GPU arrays. We see some differences in the computation just because we've enabled the use of GPU array with the zeros function, but you can see here the work that we're doing between the two scripts are identical, right? And the last thing that we have is this gather function, which calls back the results from the GPU memory when we finish. And because of how long the actual demo takes, I just want to showcase a video for this with you, and kind of skip a little portion here. But we see that the video is sped up, but we can still see a drastic performance difference between when running this problem on the CPU versus when running the problem on the GPU. And if we actually skip to the end here, I just want to show here we reached the iteration step size that we wanted to stop at I believe 200,000. But with the CPU, we barely reached 10%, not even 20,000. So significant increase in performance here. And that's because we're leveraging the right tools and the right resources to be able to get to this point. So the workflow that we just covered, right? The first step is going to be creating the data that you actually have access, that you actually want to work with, or getting access to it. The second step is transferring that data to the GPU, and this is handled for you using your GPU array. The third step is to perform your calculations like you would any other array. And then lastly, just to call gather on it to gather the data from the GPU. And one really cool thing about GPU arrays, really any of our data types in MATLAB is if I go ahead and clear this, I say A is equal to GPU array of 10. I do methods of A. Right, we have access to all of these functionality that are supported with our GPU array. You could look at our documentation as well, but I just really want to show you this because I think it really gives you a good idea of just how many functions we've enabled to use GPU arrays with, so how supported you are if you wanted to go from using the CPU to GPU. You can do the same thing for tall arrays as well, and you can also look at the documentation for what is GPU enabled, but this is also another method. Again, the last option with programming with GPUs that give you the greatest control are things like SPMD, ArrayFun, so on. For most of you here, you probably won't need access to this advanced capability, but if you do, again, please feel free to reach out to anyone on the MathWorks team, Sumit especially, so that we can get you geared up for success and match with the right people. Yeah. And Sumit will put his email ID and contact information in the chat so that if you do need to reach out, you have his contact information. So a quick summary of everything. Really, the main sentence that I want you guys to remember is that it's very easy and it's very easy to leverage our parallel tools, and if you leverage them correctly, they're very powerful in helping you speed up the work that you need to do. We have other points that we went over, such as the fact that you don't need to be a parallel programming expert to leverage our capabilities. We have a lot of documentation to help you out with them. You don't need to reinvent the wheel. You can just get started with the examples that we have. And you can begin your work locally and then even scale up to clusters or even the cloud when you need to. We have other valuable resources. I think I've talked about the documentation plenty of times, but here is the documentation again. We have other tutorials that we have as well. And so I actually just want to open this up real quick. And so you have access to different videos that showcase how to actually use the code and our functions. And you also have the capability to download all the example code for these tutorials. One last thing I want to kind of go over before the end. So we saw programmatically how we can enable the parallel pool using our pool here. So you have a lot of programmatic access, but for those that, again, wanted to be a little bit more interactive, you could easily just go ahead on the bottom left-hand corner here where these bars are, and then just click, and it allows you to enable or shut down your parallel pool and set your preferences as well. So as I'm wrapping up this presentation, I'll go ahead and shut down my parallel pool. So that's going to be it for this brief presentation and demo on how to speed up your code in MATLAB using our parallel tools available to you. If there are any questions that came up, please put them in the chat and we will address them after Lisa's presentation and San Diego Supercomputing Group's presentation. Thank you.
Thank you very much, Tim. And everyone, thank you so much for being part of this talk so far. Please continue sharing your questions to the Q&A panel. And at this point of time, Lisa, I'd like to invite you. Do you want to take over?
Hi, everybody. Thanks. I'm going to try to share my screen. Can everybody see? Yeah? Okay. So I'll get started. Thanks, Sumit. Thanks, Tim. Great job. Just put this down here somewhere. Okay. All right. So I'm going to change gears a little bit here and talk about science gateways. And that's a little different than Tim's presentation. We're going to be at a higher level talking about some of the capabilities and available via online portals for researchers and educators. MATLAB is used a lot in research, and there's a lot of things that are available for doing research with MATLAB. On our site, you can find information on this page about how researchers are doing climate research with MATLAB, or another big trend, obviously, is the work on COVID. There's a ton of researchers out there researching COVID and related things about aerosols and even the economy and all kinds of things with COVID. Information on AI and how to use it, and we just heard about parallel computing, obviously. So all kinds of things, and not to mention the ability to do open science. And one of the ways that researchers do open science is through the use of something called science gateways. Now, SDSC is actually the home to the Science Gateway Community Institute, or SGCI. So some of you may be very familiar with what a Science Gateway is, but some of you may not. And so I'm going to try and explain a little bit about Science Gateways and how they tie to MATLAB and work that we're doing to work with Science Gateways. And for those of you who have labs, meaning you run a lab or you work in a lab, or those of you who are a part of professional communities, this is related to you in that way, because perhaps you could make use of some of these concepts. So one way to think about Science Gateways is they're online portals that researchers and educators use to share resources and find resources that other educators have put up. And especially with all this move to online, and just collaboration in general, it's a great thing to have places where people can share. But what is it that they're sharing exactly? And so a short list and top level categories of what they're sharing is data. So you might be in a certain discipline and maybe you're sharing data for that task or the domain that you're involved in. People share papers, of course. There's all kinds of sites that have research papers. People share code and obviously offer compute, as you guys do on SDSC. And then there may be tools for learning, whether it's for getting familiar with something general like AI, or something specific, such as the area that someone is working on, say biology. People share curriculum, and also just lots of different code examples that are up for people to learn from each other. So I'm going to be talking about some science gateways where MATLAB is in use, running through this list. Okay, so one example that I'm going to start with is tied to data. There's a site called HydroShare, and HydroShare is a place that hydrologists put content that they want to share with other hydrologists. What you see here is an example where there's data on the site, and here's an example that somebody made that's actually a MATLAB live script that works with that data that's on the site. So you can go to this page, it's called a resource, and you could open that resource with MATLAB Online, and what you'll see is a MATLAB live script open on that site, showing this thing that Anthony Castronova has put up. And you can see they've actually got a MATLAB running on their site. So what's more interesting that they have the resources that they can run MATLAB, more interesting than even that, is how many times that this thing has been viewed. You can see almost 3,000 times people have come to see this example. Maybe they're interested in rainfall and how to measure rainfall. And also some people have downloaded it so they can run it on their desktop. So that's a data example. Here's another example where CodeOcean is allowing people to post code tied to research papers. And so it's like HydroShare in that it's easy to navigate and searchable, and you can download the things that you find. So you can go and explore, they're called capsules, and here's a list of some capsules with MATLAB, and this one you could open and you could run it. And again, it's code, and you're running the code. They've provided the data there if they want you to run it so that you can see it, and you can see it produces graphics. So that's another gateway called CodeOcean where people are putting up code usually tied to research papers. There are two other gateways. One is NanoHub and the other NSG, and these are actually on SDSC's computers. One is NanoHub for engineers and nanotechnologists, and we worked with them, with NanoHub, MathWorks worked with them to to run a webinar, and we had a lot of registrations, as you can see today. A lot of people came, but this had even more. And then there were many users of the NanoHub, of MATLAB on NanoHub as a result of the webinar. So that's the sort of thing we do with partners. In the case of NSG, or Neuroscience Gateway, you can see here that MATLAB and EEG Lab are running on Expanse, which you'll hear about from SDSE, I believe, in a minute. And so there are perhaps other opportunities to have things that neuroscientists need on NSG to help them use the capabilities on NSG, the compute that's there. And you can see there's two here. So that's the sort of thing we do, sort of either the site sets it up themselves or they work with MathWorks to help set it up. Now, what is this EEG Lab thing I'm talking about? So this is a good segue into not just compute, but what is it that people are sharing? So EEG Lab, it says right here, is an interactive MATLAB toolbox. So this is not made by MathWorks. This was made by the community, meaning community of neuroscientists. And they've said, hey, to do a good job with neuroscience, you probably need this special code if you're doing this sort of thing, working with electrophysiological data. So it's very popular, and we'll see that in a second. So where is it? Who owns this thing? Where does it live? So if you come here, this is called File Exchange, and this is on MathWorks site. And people can put up whatever code they want to put up on the File Exchange. And you can see here that this EEG Lab on File Exchange has had 13,000 downloads. It was actually apparently updated just about a week ago. But really, it lives on GitHub. You can download it from here, but it lives on GitHub. So if you go to GitHub, or if you click on the download, what you're really pointing to is this GitHub repository where EEG Lab lives. And you can see that people have been working on it over the past year and previously. You can also see that it is very popular, because when something has a lot of forks and stars, that means people are liking it, essentially. And so that's what EEG Lab is, and it's representative of the kinds of things that you can find on File Exchange or GitHub, things that are created by the community, code in this case. There's more than that. If let's say you were in neuroscience, maybe you're not, but if you're in neuroscience, so there's more than just the EEG Lab. If you go to File Exchange, you can see that there are 659 things specifically tagged as neuroscience, and you can see on the left there some specific areas that those things cover. So if you're a neuroscientist, it would be a good idea to come to File Exchange and look around and see if you can make use of any of those 650 things. And there are other sites besides File Exchange, as I said, GitHub and other places where things might live, but we encourage people to put entries into File Exchange so that if someone is searching in File Exchange, they might find that neuroscience entry. Okay? So that's a little bit about community code and people sharing it on various sites. We could call those science gateways for this purpose. All right, and there's one other site I wanted to mention, and this is for curriculum, and it's called SERC, or Science Education Resource Center, and there's a whole site there devoted to teaching with MATLAB. And in addition to having, information, it says here data analysis and how to teach computational thinking and all kinds of other strategies for teaching. In addition, there's these teaching modules are called teaching activities. I don't know if you can see that, but it says there's 223 separate activities, and on the right here, they're divided into groupings, maybe by, again, discipline, biology, chemistry. So if you were an educator looking for problems to use in your course, you might come here. And so this is a Science Gateway, a portal where educators post modules for other educators to find. And so that's another example of a Science Gateway or portal for sharing. So if you had a place that you were trying to teach something, whether you're trying to share content and show everybody that there's all this content for your area, or maybe you're trying to teach, in this case, statistics and machine learning to people, you might say, so what MATLAB things would be relevant to sharing this information with people? So I made this example where, well, if you were doing that, you could learn MATLAB using the MATLAB on-ramp. That's actually a course you can take, and you can link to it and take it for a couple hours online, or you might link to the machine learning on-ramp, which is also a course with MATLAB for doing machine learning. And so, or maybe you have examples for code examples. I did not fill it in, it's left blank. Or maybe you have, other algorithms or toolboxes. And so you could imagine that if you're trying to convey something to, some community, that you could set up your own little mini portal for that topic. And I'm happy to talk with anybody more about this, but it's under the category of skills training. So in summary, and I just had 10 minutes of information to cover with you. So in summary, these gateways are portals where researchers and educators can share information. And whether you're collaborating or looking to build a course or figuring out how to do your data analysis, it's all in service of getting everybody up to speed on some area that they're working on. Many of them work with MATLAB, as you saw. There are different types, and whether it's code or compute or whatever, and centers like SDSC are continually improving their offering. So if you have a lab or a site that you own, and you're wondering, could MATLAB be integrated better into that site? It's something for you to think about. I'd be happy to talk more with you, as would Sumit and others from MathWorks. So I thought I'd put that out there and let everybody, think about it and get back to us if you have questions or ideas for how to improve gateways. And that is it. So I'm looking forward to hearing your questions after the talks. Thank you for listening.
I'll take on. Thank you very much, Lisa.
It'll be a little bit convoluted here, but so if you share screen and then go to that first link, we'll just go. So everybody, thank you for your patience. I'm Mary Thomas. I'm the HPC training lead at SDSC, and I work with Susan, and we put together a lot of the training events. So I just wanted to, can you go this is the session that we're in, but I also gave you a link to just go to the main training page. Yeah, we'll just go ahead and stay with the Expanse portal. So what I've got here, it's always good to have a backup plan for when things go wrong, and that's where we are right now. So go back to that portal page. We'll just stay there for right now. So what we're going to put into our link is a pre-recorded overview of using the Expanse user portal. And if you could type that link into the chat, I'd appreciate it. Timothy, then people, you can go here. We have a series of interactive videos, and this is one of them. What we do is when we hold an event, and we'll do it with this event as well, is we get a copy of the presentation, and we get a video, we get the transcript, and this video is searchable. For example, Timothy, if you were to scroll down below the black box, and under transcript search, type in MATLAB, you see transcript search under the black video. Okay, yeah, just type in MATLAB and it will tell you where MATLAB is mentioned in the Expanse user portal. So this is a short 17-minute video about how to log on and shows you all the interactive services that you can run on the portal. But in the video now, what you can do is if you click on like at 1540, start the MATLAB job, just click on that entry. And then scroll back up and show the video. It will jump you into that part of the presentation, so you can go right through all 17 minutes and go find, okay, where's the one on MATLAB? But we also show you how to use Jupyter notebooks and other technologies, and there are ways to launch MATLAB through the Expanse user portal and also from the command line. And this one focuses on the portal. So I wanted to make sure you knew that you can run MATLAB on Expanse, and it's pretty easy, especially in the portal. So Timothy, if you go to a new tab and type portal.expanse.sdsc, EXPANSE, this is our HPC cluster, .sdsc.edu. sdsc.edu. Nothing like typing in front of like 100 people. Oh, so it would make you log in, and I can't demonstrate it for you. So let's just go back to the video. Um, so I'm sorry, I can't get you guys in. You can make an account and get allocations, but again, if you're an Expanse client, and we're really hoping a lot of people from the Expanse community or SDSC community are here, then you can get into the portal and run MATLAB very easily, and you can see it all in this video. So I can't do a live demo. I apologize for that. But you can get back in touch with us and see this video, and there's a few other training materials that we have that allow you to learn other things about running jobs, how to get onto Expanse. And I'm going to put this into chat to share as well. Where is the chat? And then maybe Timothy, you can open up a lot of you probably saw our training page, but just in case you didn't, if you would go to that link that's in the chat, Timothy, I'd appreciate it. Yeah, this is our advanced computing training. And what we have is, if you scroll very slowly, we have all the upcoming, like here's the parallel and GPU computing with MATLAB. But also, if you keep scrolling, you'll come down to our catalog. And the catalog, there you go, is all of our past events. And a lot of these are now converted to these interactive videos I just showed you. And so we're trying to maintain provenance of information so that you could go, have they ever talked about MATLAB? Oh yeah, there's 2 or 3 events in the past, and they're mostly current. If they aren't, then you'll know from the date. But you can access every one of our past events. So for example, the Triton Shared Computing Cluster is specifically a hotel condo cluster for UCSD researchers where they buy hardware. And we had an interactive computing workshop on that. And we did the same thing for interactive computing on Expanse. So you can find different tech topics, and these are all open. You don't need to log in to use them. You're welcome to browse through them and get additional training. And I think that's my overview of our HPC training and MATLAB on Expanse. In the TSCC, I wanted to point this out. There is a specific example of, in one of my talks on interactive computing, on running MATLAB from the command line on TSCC. So again, you can go through, click on the recording, it will take you to the interactive video. And there's this is a different interactive video, so we have to find the interactive video link. It looks like it's missing. Live demos always, I will check on that. Make a note. So 99% of our web recordings have a connection to the interactive video, and we're working on getting the rest of them. So anyway, thank you for your time, and I'll turn it back over to Timothy.